another epic 5-setter. He beat Kokonakis 5-set comeback, and so he's through to the third round. But it was apparently it was the second longest match in Australian Open history.
Greetings. This video is about my A700 restoration, which I started about November 2022 with great enthusiasm, since I love doing this kind of thing. After about 8 weeks, I had every single part washed and reassembled and the electronics recapped. It fired right up and it worked okay for a matter of minutes, and slowly things started to go wrong. It turns out the A700 has an integrated circuit that is subject to deterioration and failure. So 3 of these ICs failed, and although I can buy new ones for around Australian $230 each, I decided it wasn't worth risking new old stock. Instead, I thought this was a perfect application for an ESP32 microcontroller. So this is how I got that to work. The first thing I wanted to do is make sure we all understand how a tape recorder works, since I know that not everyone watching may be familiar with this. So basically, you put tape on this side, you thread the tape through, and you can play and record. Now, when you play or record, the tape speed is guided by a capstan turning at a constant speed right here. And then there's a rubber roller that holds the tape against the capstan. The reels only serve to hold the tension on each side. So each reel motor uses the tension arm nearby to understand how much tension it needs to pull. So the specifications dictate how high these rollers need to be at each side. When you want to fast wind or fast forward, the pinch roller drops away from the capstan and the tape is free to move solely from the reel motors. However, in that case, the reel that's doing the pulling uses the opposite side tension arm to understand how much tension it's pulling on the tape. So the reel that's taking up the tape pulls about 4 times harder than the reel supplying the tape. So the reel supplying the tape has to provide some drag in order that the tape remains wound tightly. Obviously, we have the motor on the left and the right. The left is called the supply and the right is called the take-up. There's a set of brakes on those 2 motors, which are operated by a solenoid right here. The brakes are not very powerful. They just put a drag on the reels so that they'll slow down a bit quicker. But they're designed to be overridden by hand. If you wanted to turn the reels for threading and whatever, they're just very gentle brakes. Next, we have the head block. So in the head block, we have an erase head. Then we have an optical tape sensor that is just a light and a photo transistor that determines if the tape is there or not. Then we have the record head, then the playback head, then the capstan, and this item here and here are called tape lift devices. They hold the tape away from the heads when it's fast spooling, so you don't wear the heads. On the left and the right, we have these tension arms that pivot. Each tension arm has a little device that turns the angular movement into a voltage output, 0 to 3.1 volts. On this side, this roller here has a function of indicating that the tape is moving. So obviously, we have the 3 motors. They're all of the same type, but I would imagine the capstan is a slightly different wiring. But they're all the same type of motor. They're called AC torque motors. They run from single-phase AC, but they can run happily right down to a stall without overheating. They're quite specialized motors, but Revox tape recorders have always used this type, at least the consumer-level machines. You can see the die-cast chassis. You can see the 3 solenoids that operate the brakes, the tape liftoff, and the capstan pinch roller. And then this board in this area are the tape transporting Capstone speed control. And then down here we have the audio input and output connectors and the headphone amplifier. The main audio electronics sits in this area right here. This is the Capstone motor drive circuit. So what Revox has done is pass one leg of the motor through a bridge rectifier, which is connected to a power transistor. By adjusting the bias on the power transistor, you're effectively introducing a resistance into this leg of the torque motor, which slows it down or speeds it up. This is the Capstone speed control circuit. The Capstone's AC torque motor has a variable reluctance tachometer on it, which provides a weak AC sine wave across this capacitor. That sine wave is high-pass filtered, amplified, and then processed into a square wave of minus to plus 10 volts. That is fed to the next IC, which is the TCA561 frequency and phase comparator. The input of that IC shaves off the negative portion of the signal and limits it to plus 5 volts. The TDA has a crystal of 1.6384 megahertz, which is divided down depending on which push button you select to either 400, 800, or 1600 hertz. When the tachometer frequency matches one of those frequencies as selected, the TDA outputs a sync signal, which syncs this amplifier and lights up one of the three bulbs to indicate the speed you've selected is synchronized. The output of the TDA at pin 7 is a signal from 0 to 5 volts that represents the speed error. So if the tachometer is running too slow, the signal is 5 volts. If it's too fast, it's 0 volts. If it's at the correct speed, the signal has a PWM percent that represents the phase difference. So the ideal speed of the tachometer, or the Capstone, is when this signal is at 50% duty cycle. So this signal is smoothed through this circuit here down to just a DC signal. It's then divided into a much smaller amount and set over a reference voltage of about 0.7 so that it suits the input required by the TCA561, which is the servo error amplifier. This IC takes a reference signal determined by this trim pot in here, compares the incoming tachometer, actually the speed error signal, and outputs at pin 7 a motor drive signal, which is analog, through a 100 ohm resistor going directly to the base of the power transistor that I discussed earlier. So this is the IC that has failed, along with the other two on the transport board. So my ESP32 microcontroller takes the same signal at pin 3 and outputs the required signal at pin 7. But in my case, I'm using PWM instead of a linear output, simply because it seems to work just fine and it runs cooler, it's more modern. This is the A700 transport control board. It's centered around a custom IC, which is TTL level. It takes in all the push buttons that are on the front panel. It provides interlocking. It lights up the indicator lights. It provides signals to the solenoids, the tape lift, pressure roller, and brakes. And it sends logic signals to the two TCA561 ICs, which are the motor servo amplifiers. So each of these controls one of the spools, one of the reels. It takes a signal from the tape tension arms, right and left, which is just an analog signal is 0 to about 3.1 volts. It takes in all the logic signals, and the result comes out on pin 7 into a transistor circuit intended to amplify the output of the TCA into a full range of bias current for the power transistor that's driven right from here, pin 7. So in my implementation, I've had to replace the function of this entire part of the circuit. So I've taken in 7 logic inputs, the 2 tension arms, and I'm outputting a signal directly to the power transistor. I'm ignoring the drive circuits here. This is how I associated the A700 IC pins to the ESP32. In this page, I've documented the timing of the transport logic. So this is what happens when you press the buttons on the front. These are the signals that go to the servo amp chips that I have to interpret to know how to drive those motors. So what I have here are, these ones are the buttons, and these ones are the signals to the servo amplifiers. So in this particular sequence of operation, I press play, and then fast forward, and then fast rewind, and then play again, and then stop. So this shows you what the signals do. When you press play, the play signal goes high for the duration of play, right up until you press fast forward, which drops you out of play. When you press fast forward, that turns on both fast wind and the fast forward modifier. Next, I'm pressing rewind. So when I do that, the fast wind signal stays on, but the rewind signal now replaces the fast forward. When I press play, the fast wind signal drops off, as does the rewind signal, and now the play signal returns. When I press stop, the play signal drops, but more interesting is that this signal called TME, which I believe means tape motion on, it stays on for some period later. And what it's saying is that the transport has to break to a halt. So when play exits, there is a period where TME stays on. That is the time when the reels are going down to a stop. So that's what I call e-braking here. So I have to know to make the reels go into a braking mode. I used pin headers, same as that you use with your ESP, and I just simply plugged a row of 8 into each side of each socket, and then I put some perf board on top, prototyping board, and then I laid a ribbon cable on, 16 pin, and I attached it with double-sided tape. So here's an overview of the ESP32 prototype board. The input power is 24 volts DC. It comes in through the top here, and I take that directly from the A700 power supply so that I don't load any of the wiring in the machine. 24 volts goes through a fuse and then to this switch mode buck converter, which is set for 7.5 volts. 7.5 is to drive each of these 3 amplifiers. It also drives this linear 7805 to provide 5 volts to the ESP. The amplifier outputs go through resistors just like they do in the original circuit, 100 ohms for each real motor. I used 82 ohms for the Capstone because I used a different power transistor from the standard. And that's a Darlington, so I had to drive it with a little bit more voltage. All the motors are connected to these pins, 6 pins, through a twisted pair right up to the power transistor circuit boards. The inputs to the ESP all come in through this header block, which is obviously attached to the ribbon cable. I had to look at all the inputs to scale them to suit the ESP32, meaning voltage dividers as needed. Many of the logic pins are 24 volt logic, so I had to knock that down to about 3 volts. The tension arms are already exactly conveniently at 3.1 volts. So these are all voltage dividers to suit all those logic inputs. This connector is for my little remote control that I use to make adjustments on the fly. It's a temporary remote. It won't normally be left in there. I've got connectors for the boot and enable switches so that I can load the software and restart the ESP remotely, basically from the front of the machine. I'll briefly cover what I did in the sketch to make this work. Anyone who's attempting this should familiarize yourselves with the auto PID library. So in the way I've done it, I created 5 auto PID objects. The Capstone runs by itself. It's independent of everything else. It has its own. Then I have 2 each for play, basically the left and the right motors, and 2 each for fast wind, left and right. I'm treating fast forward and fast rewind the same. They're just the reverse. One is just the reverse. In the constants, you need to declare all your parameters. So you have a speed offset. The speed offset is because the signal coming in from the Capstone, the TDA1000, is an error, not a direct speed feedback. You have to reverse it. So I take the value and I subtract 820 so that now it's actually a speed. So when the error goes up, it's effectively the speed goes down. In the end, that value for the feedback needs to be in the range 0 to whatever, 4,000 or whatever you like. Then I have a demand. So I want the Capstone to run at this speed. Now this 150 actually represents 50% PWM coming out of the TDA1000. You determine that by putting a scope on the Capstone controller board. There's a test point for that. And you can watch the output of the TDA and find what speed demand gives you 50%, or approximately. 40 to 60 is fine. So for the Capstone, I have the 3 parameters: proportional, integral, differential. Now, just getting on to the real motors, the tensioners provide a signal that is higher with more tension. So I also have to offset these because I want the signal to go in the other direction. When I have more tension, I want a lower number. The 10-bit input, I just subtract 10 bits from that and I get the reverse number. The play mode set points, this actually, the 650 represents tension. The take-up has a higher tension, 880. This is to meet the Revox specification for the angle of the tension arms. It's laid out in the service documentation. You'll note the PID parameters are quite low for these. They don't need to be high. It's a very easy application, pulling the real motor tight. There's really nothing to be read in this proportional number. It's just a scale between what's coming in and what's going out. But we do note that the integral and differential terms are quite small in comparison, which actually is expected because the original Revox design would not have had a lot of these two items in it, and yet it works. So this auto PID is really a lot more sophisticated than what Revox originally supplied. Now in FastWind, the supply reel is defined as the one supplying the tape, and the take-up is defined as the one taking on the tape. So you're always going to require more tension on the take-up side than the supply side. Again, the PID parameters are quite small, and there's no integral and differential. So the PID objects, there's the 5 of them, as I mentioned. They don't all run just because they're declared. You simply define them, and then you invoke them as needed. So we have the normal stuff in setup, all the pin configurations, but there's a couple of extra relevant to auto PID. The first one is you need to set the calculation time in milliseconds. The default is much too long for auto PID. I think it's about 1 second. So you need to set the time step to 1 millisecond is appropriate. So each of the 5 auto PID objects have a time step set to 1 millisecond. That means that when you run that object, when you use the run property of the object, it will recalculate every 1 millisecond. So you'll have to call it more rapidly than 1 millisecond to get that to work. So in the loop, the one important thing to do is to offset the tension arm signals. And when I say offset, I actually mean you reverse it. Because, as I said, the tension arm signal, which is here, is moving in the wrong direction, so I need to reverse that. I then call these functions at full speed, and I have this other function I call soft spot, which runs at 25 millisecond intervals. All it does is provide a controlled tensioning of the reels to avoid the tape being left loose at the end of a transport function. Like, for example, when you press stop after play, sometimes the reels will leave the tape a little bit loose around the rollers and the arms. This little item here, if I set this variable to a number, like 100, this function will apply torque directly, request torque directly from the two motors, and then decrement it down to 0 over a short period of time. In this case, 100 times 25 milliseconds. Then I have functions that detect the various transport modes. And within each of those modes, there are segments that have to be looked at separately. So, for example, rewind initialized. So this is nothing more than if statements that look at all the transport inputs and look for the combinations that indicate that rewind has been requested. When I see that, I set a flag, and then I zero out the PID calculations for the left and right motors, just in case there's something residual left, keeping in mind the calculation only runs when it's asked to run. And then I just print to the console that it was initialized. The same thing with fast forward, it's identical. Except on both of these, I set a flag so that I know that I've completed this step. Then I have rewind ongoing and fast forward ongoing. So what I'm doing here is setting which motor is the take-up and which is the supply. So in these two instances, they're reversed, depending whether you're going rewind or fast forward. In both cases, I need to invoke the run property of the objects in order for it to recalculate the values. It may not update them if it hasn't hit a 1 millisecond increment, but you need to invoke this property whenever you expect this thing to work. And lastly, I'm issuing the output of the auto PID object to the motor using the digital to analog outputs. And remember, there's two of them on the ESP32. I'm using both. So all I'm doing is taking the left and right motor torque values at that moment and issuing them directly to the 8-bit DAC. Now there's a braking phase when you're in fast wind. So again, there's a combination of transport inputs that will tell you that that's happening, namely TME. TME tells you is present when you're in the braking phase, while other items are not. For example, there's no fast wind, but there is TME. There's no rewind, and there's no fast forward, but the brake flag, rewind brake flag, is present. So in this case, what I've done is now reverse the roles of take-up and supply. So for braking, from rewind, I've switched around the supply and the take-up from the left to the right because the motor torques are simply the same, just reversed. So again, I have to run this property of the object, issue it to the DAC outputs. So fast forward, rewind, braking, the only differences are what flags and inputs it's looking for. It all works the same. Then I have exit. The reason for having an exit is to zero the motor control output. So I'm just simply directly writing to the DAC pin 0. Then I reset my brake flag so that I know it's done. Now I'll just add that there are other functions that I haven't really discussed. Pause is one, where in any of these functions you can press pause, and while you hold the button, it will pause that function. So you have to, if you want to do everything, you need to detect that situation. Play is not too complicated. It's much the same. You initialize it by detecting the required inputs and the absence of a play break flag. Then you set the play break flag so that you know you've got to this point. I zero the other flags just in case they happen to be left set. Then again, I reset the PID objects just in case there's some residual numbers left there. I don't want anything to be suddenly applied to the motor that is not part of this event. So then I have other situations from play. One of them is where pause is pressed. Others are when fast wind is requested directly from play. And the more normal one where you transition directly to stop. So, and that is the one where I use the soft stop. So by setting this variable to 100, over 25 milliseconds, I'm applying a torque to both motors, equal torque, that decrements to 0 and just keeps the tape tight against the tensioners so that it doesn't look sloppy. The Capstone is very simple. The same thing here, we do this offset to turn the signal in the other direction. We run the object. We have to do that more than every 1 millisecond. And then we write in PWM to the pin. And I'm using 5 kilohertz as the PWM frequency. It seems to work fine. It makes no noise. I haven't had the slightest problem. Now, one of the functions I'm calling at 25 milliseconds, I don't need to call this in full speed because it's just not that critical, is where I read the transport inputs. So here I read all of the pins coming in. I have to invert most of them, if not all. I then detect edges so that if necessary, I can print to the console what just happened. In this case, I have these all commented out because I'm done with them. But the idea of this function is to simply set variables to the state that the transport is requesting. And that's really the whole thing. Thanks for watching. If you got this far, you've done well.